Okay, so this screencast is on the binomial expansion. We've had a few days on this in class, and we've looked at some various things, but no recordings to date. So it's time to catch up and just I guess summarize some of the things we've been doing, and hopefully help with your understanding of the whole topic. That's the idea of all this stuff. So the binomial expansion, binomial two-term expansion. So this all kicks off with, what is the expansion of a plus b to the power of n? What do we get from it? Well, if you remember back to the Cook theatre, we took to the power of 0, and as we do with a lot of things in maths, we start out small and we look for patterns. That's what mathematicians do. They look for patterns. And oh my goodness, with this there are some patterns. So when we go across here, we go, yeah, well that's just equal to 1, isn't it? That's 1. That's a plus b. That's a squared plus 2ab plus b squared. Right, this is great. A cubed. It's those of you who got round to this, 3a squared b plus 3ab squared plus b cubed. No one could be bothered with the fourth, but by the time we collected the coefficients, which is all we did here, 1 there, 1 there. Right, the coefficients, the 2, the 1, the 3, the 3, the 1. Right, we put all these down. We discovered we had a nice little triangle of coefficients emerging. Each time, each expansion, one more term, power 3, 4 terms, power 4. We're going to have 4 terms. And at this stage, we said, no, hang this. I can see what's going on here. That's going to be a 4. That's going to be a 6. That's going to be a 4. That's going to be a 1. So I reckon my coefficients here are going to be 1, 4, 6, 4, 1. And in here, we're going to have a to the 4. Then we're going to have a cubed b. Then we're going to have a squared b squared. Then we're going to have ab cubed. Then we're going to have b to the 4. Wow, look at that. In about a minute, we've sorted out our binomial expansion. We've picked out a lot of stuff already. We've got this fantastic thing here, the Pascal's triangle. If we sum the rows, we get this thing going on, which is 2 to the power of n. If we have a look at, so this is our fourth power, 4 is the second element along, we call it the first actually, and 2 to the power of 4 is the sum of that row. So this is all going great guns at the moment. We've got this palindromic situation where it's the same forward and back. It's symmetrical. If we go and color in, I looked at the patterns, the Sierpinski's triangle. You can go crazy with this. Your explorations, you might want to look into this because there's so much in Pascal's triangle. Anyway, don't get carried away. Let's get back to it. So what we've got here is a Pascal's triangle, and that's going to assist us. It's already assisted us. It's given us this a plus b to the power of 4. I'd still be doing that if it wasn't for Pascal's triangle. There's no way I'd have finished that by now. So anyway, we got to there, and then we thought, all right, well, what if we want to expand power 10, power 12? How are we going to do it? Because I don't want to keep going. My page isn't big enough. I really don't have the, I love Pascal's triangle, but seriously, I'm not going to go down to the row 12. So what is, can we find these numbers another way? So yeah, all right. So we started looking at, well, how do we do that? This is, if we call this row 0, and we call this row 1. This is row 2. So if we think about that, and this is position 0, this is position 1, position 2. Now this is row 4, so the row is the same number as that there. It's bookended by 1s, fantastic. Okay, so the codes for finding these numbers are row followed by position. So this number here is row 4, position 2, so that's 4-2, or 4C2 on the calculator. 4C2, I've already got it there. There it is there, 6. So let's just check, is it 6? Yes, it is 6. So for a plus b to the 12, then we could go and we could find out the 12th row just by putting 12C0, 12C1, and so on. So what we found from this, just a couple of little things about this 4C2 business and what have you, this sort of notation, this NCR notation, is that we discover that n0 is always equal to 1. That's the position 0 there. As we found out about nn, that's also equal to 1. What else did we find out? We found out that n1 is equal to n. That's just that one there, 4, 1, 3, 1. Did we also find out that nr will equal n minus r? Did we find that? So, for instance, we did an example, didn't we, where 12, 5 was equal to 12, 7. So if r is 5, n minus 5 is 12 minus 5, which is 7. So that's the symmetrical property we were talking about before, where we've got this equal to this. Okay, so there's some nice little results. It's all going absolutely superbly. Right, so now we've got that, and we just then looked at, well, all right, can we come up with a general term for the binomial expansion? So we got our friend sigma out, didn't we? And we said, okay, we could say that a plus b to the power of n is equal to the sum of, from r equals 0 to n, nr a to the n minus r, b to the r. Beautiful. 3 elements, 1, 2, 3, 3 elements to each term. And then we set about doing some things, some expansions. And now we've started looking at specific terms, and what's the coefficient of x to the 5 in blah blah blah. And and today we looked at some tougher ones. I want to find the constant term in the expansion of, and in question 9, in the expansion of x plus 1 to the n, the coefficient of the x cubed term is 2 times the coefficient of the x squared term. Find the value of n. That's tough. So I reckon I did 4, 7 on the board today. I'm going to do 9 now. Question 9, just to, if you think you can do it, fantastic, go ahead and do it. Well, if you haven't had a go at it, have a go at it now. Come back, pause the screencast, come back to it. I'm going to have a look at it, because I think it's quite tough. And then 10 is very similar, and you can have a go at 10, and you can prove that you can do it. So 9, in the expansion of x plus 1 to the power of 9, sorry, to the power of n. That's the point of this. Power of n. The coefficient of x cubed is twice the coefficient of the x squared term. Righto. So I'm going to write this as the sum of, from r equals 0 to n of x. No, not x. We're not ready for x yet. It's not ready for x yet. Come back. We're going for n. Now it's x to the n minus r 1 to the r, which is not very interesting because 1 to anything is 1. I'm actually, so what's my value? Well, I want x cubed and I want x squared, and so I don't really know about this because I don't know what n is. So I'm going to turn this around, and it's okay to do so. I'm going to turn it around so it reads nr 1 to the n minus r. Again, big deal. X to the r. So for x squared, r is equal to 2. So that term is n2, 1 to the power of n minus 2. Again, that's just 1, x squared. So therefore, my coefficient of x squared is n2. Excuse me. I'm going to do the same for x cubed. Make r equal to 3. That's n3. 1 to the, I'm not going to bother with that, x cubed. So therefore, coefficient of x cubed is n3. Now, what have we been told? The x cubed term, the coefficient of the x cubed term, that n3. So therefore, my n3 is equal to twice the coefficient of the x squared term. So it's twice this coefficient of x squared term, which is n2. Right, that's my equation. I need to solve this equation for n. What's this vertical brackets? Well, I'm going to have to get that out and put it in in factorial notation. And a little reminder, and it's on your formula sheet, that NR is equal to N factorial over R factorial N minus R factorial. All right, so that's we're going to have to use that now, because this N3 is N factorial over 3 factorial N minus 3 factorial. All right, I'm going to have the 2 out the front here. It's going to be 2 by N factorial over 2 factorial N minus 2 factorial. Okay, so now I've got, I've got an equation to solve. This is fine. I've got 2, 3 factorial, but this N minus, all right. The way to solve these equations with factorials in them is to start writing them out and just see what's, there's going to be loads of cancelling. Let's just go ahead and see what happens. If you think you can pick it up at this point, just any time, just pause and go for it. Remember that factorial notation is multiplying by 1 less each time. I'm just going to give it a few there to give the idea. 3 factorial, that's 6. And n minus 3 factorial is n minus 3, n minus 4. Remember taking just 1 off each time. Alright, now that's equal to 2 by n minus 1, n minus 2, n minus 3 onwards, over 2, n minus 2, n minus 3, n minus 4. You get the idea. We're taking away 1 each time, all the way down to 1, the dot dot dots. But we're going to get rid of these dot dot dots now, because this fantastic thing happens here where, look at this, the n minus 3's all the way down forever back to 1 or cancel. So we're now left with some algebra here. Fantastic. N minus 2's, 3's, off you go. Done. Even these 2's are gone. That's beautiful. Look at this. Also, the n and the n minus 1, I can divide that both sides by n minus 1. Both sides by n minus 1. On the right-hand side now, I've just got 1. Look at that. Everything's gone. On the left-hand side, I've got n minus 2 over 6. Remember that n minus 5 is gone as well. There's an n minus 5 up there somewhere. N minus 2 over 6 equals 1. Therefore, n minus 2 equals 6. That was a bit scrappy. N minus 2 equals 6. And therefore, n equals 8. Fantastic. So the value of n that gives my coefficient of x cubed twice the value of x squared is n. And we can check it. So x plus 1 to the power of 8. Now put 8 in here. 8, 2, and 8, 3. You'll find one of them's 56, one's 28, and that will be verified. So try question 10. I'll see you in class tomorrow. Hope this has been helpful.